Hi guys, today we're going to go through some quantitative chemistry. I know a lot of you have been asking about the types of questions that will come up in your GCSEs, so I've picked a range of questions from level 1, which is like your foundation tier questions, level 2, which is top end of foundation and entry to higher tier, then level 3, which is higher tier only, and then a triple one, which you'll see is not that different to higher tier really. And I've tried to pick questions which are actually a little different than you might do in class. Those ones that students say, I couldn't get it, I didn't know, I couldn't understand what I had to do. Those types of questions. So let's get into it. The first one is your basic MR calculation, but with a bit of a twist. So let's read it through. A student repeated the experiment with a different group 2 metal carbonate, XCO3. So the carbonate is CO3 and the X is the metal, which we don't know yet. It says that the total MR of the whole thing is 84. And it gives us the relative atomic masses of AR for each, carbon 12 and oxygen 16. And we have to calculate the relative atomic mass of X, so find out what X is, and then use the periodic table to find out what it is, which element it is. Now to do that, let's choose the pen, I'll show you how to do this. First of all, we know that the whole thing is 84. That's the mass of everything. And we've also got the masses of carbon and oxygen. So if we take them away, we'll find out what X is. So that's the first thing to do. We know that XCO3 is 84, and that's the total. So from 84, let's take away the carbon, which is 12. So 84 minus 12. And then let's take away our 3 oxygens. So you can see that, there's 3 there, and each one is 16. So we're going to take 12, and we're going to take away 3 lots of 16. And that will tell us that X is 24. And there's only going to be one element on the periodic table that you're given with a mass of 24, and that is magnesium. So the AR is 24, and the element is magnesium. Now, when you're looking at that for 4 marks, that's a lot of marks just to skip a question like that, which is relatively easy. But the tricky part is knowing what to do. So hopefully that cleared it up a little bit for you. The second question is kind of like a staple calculation, if you like. You're going to have to do concentration calculation. You're going to have to do moles. Just the way it comes up and to what degree, well, that's up to the AQA really. Now I know the concentration calculation. I know it's conc equals, in this case, mass divided by volume. How did I know it was that one? Well, I looked at the units. It said here I wanted concentration in grams, which is a mass, per decimeter cubed, which is a volume. So mass will always be in grams, or should be, and the volume for the calculation should always be in decimeter cubed. But as you see here, we've been given centimeters cubed. So that's something to look out for. The examiners will try to throw in something a little bit tricky like that to make you convert basically. So how do you know when to use concentration is moles divided by volume and when to use grams divided or mass divided by volume? And for that, I would always say, look at the units. It says here grams divided by decimeters cubed or grams per decimeter cubed. So that's when I'm going to use mass. So always use the units to check which calculation to use. Now we need to put in some numbers. So concentration equals mass, so 3.2 grams. And we need to divide it by our volume in decimeters cubed. So we're going to divide that by 50 over 1,000. Now to go from centimeters cubed to decimeters is divide by 1,000, and decimeters to centimeters is multiplied by 1,000. Now when I do that, we'll see what we get. I haven't got a scientific calculator, so you're going to have to bear with me while I use this one. So we're going to do, first of all, 3.2 divided by 0.05, which is 64. Right, the next one is a level 3 extended question. And I've said extended just because there's more parts to it. So it says that sulfur dioxide is an atmospheric pollutant. And the sulfur dioxide pollutant is reduced by reacting calcium oxide, so this thing here, with sulfur dioxide, and it produces calcium sulfite, this thing here. And I have 7 grams of calcium oxide, so I have 7 grams of this to start with. and it reacts with an excess of sulfur dioxide, meaning more than I need. And what you have to calculate is how much of this do I produce in the end? Okay? Well, I can't simply just compare mass to an unknown. I can't say, well, if I have 7 grams of this, I'm going to make 24 or 7 grams of my product. It just doesn't work like that. But what I can compare is moles. If I can work out the moles of something, a known value, I can use what's called stoichiometry or molar ratio and an equation to find the missing moles. It's a very, very clever technique and one that you'll have to master if you're after those higher marks in higher tier and triple. So how do we do that? Well, like I said, if you're ever stuck, calculate moles first of whatever you can. So we're going to calculate the moles of this calcium oxide because I've been given a mass and I've been given the ARs of the elements inside it. So mole of calcium oxide, now that should be a big C there, is mass, so 7, divided by the MR. So the MR of calcium oxide is going to be 40 plus 16. 40 because that's the AR of calcium, and 16 because I've got one oxygen there, which is the AR of oxygen. So mole of calcium oxide, and I'm going to do that in the calculator again. So I can do the first bit in my head, 40 plus 16, so 56. So I'm going to do 7 divided by 56, so 0.125. And that's how many moles of my calcium oxide I have. Now this is the stoichiometry. This is the clever bit. I now know in terms of moles, I have 0.125 moles of my calcium oxide. And if you compare it to my calcium sulfite, you'll see that there's no number in front of any of those, which signifies I've got one of them, one molecule of them, or one compound, if you like. So you've got one lot, and we call that a ratio. I've got 1 to 1. And because I know the moles of calcium oxide, 0.125, the ratio of moles for calcium sulfite will be the same. So I will have 0.125 moles of that as well. We can compare them like that. Now, it didn't ask for the moles, it asked for the mass. So we have to rearrange our mole calculation to find a mass. So let's do that. I'm going to start with a triangle because I feel like that's the easiest way to do it if you're a bit unsure about these calculations. So moles is mass divided by MR, and I want the mass. So I'm going to cover that up, and it shows me that moles times MR will get me that mass. So that's what I'm going to do. I'm going to do mass equals moles, which we now know is 0.125, and I'm going to multiply it by the MR of my calcium sulfite. Now that's a bit trickier to add up. We're going to have to get the calculator for that, but it's effectively 40 for the calcium plus 32 for the sulfur plus 3 lots of 16, 1 for each oxygen, of course. And then we need to multiply it by 0.125, and we'll have our value, our mass in grams for our calcium sulfide. So let's get the calculator up again. So I'm going to start by putting all them numbers together. So 40 plus 32, and then I'm going to have to type in 3 lots of 16. And that gets us 120. So multiply 120 by 0.125. And we get 15. 15 grams. Not too tricky. The last one you'll see is not that more difficult, really. I picked it, one, because it follows on for stoichiometry. It's that skill that we just talked about and just learned. And also because when I read the examiner's report, this was one that students just absolutely bombed on the exam that year. It was something that just wasn't answered very well. The math behind it wasn't tricky, but conceptually the question was quite challenging. So the teacher repeated the experiment with a different sample of oxide of copper. We don't know what that is. And the teacher found that the oxide of copper produced 2.54 grams of copper and 0.72 grams of water. And then it shows us two possible equations. So equation 1, where we have 2 lots of copper to form 1 molecule of water, and equation 2, where we have 1 copper to 1 water. So that ratio again, we have the 2-to-1 ratio here, and we have the 1-to-1 ratio here. 2 lots of copper to 1 water, or 1 copper to 1 water. Hopefully you can see that. Now the next part says determine which is the correct equation for the reaction in the teached experiment. If you're ever presented with an AR at the bottom here, and often some masses at the top, the first thing that should go through your head is I have to calculate moles. Even if you don't know what to do with the question, calculate moles. So that's what we're going to do. We're going to calculate the moles of copper and of water. So mole of copper. Mole, of course, is mass divided by MR. So mass of copper is 2.54 and the MR is 63.5. And if we do that calculation, we get 0.04. Okay, and we're going to do the same again, but for water this time. Water is 0.72 grams, and the MR, after adding up the 2 hydrogens and the 1 oxygen, will give us 18. And fully enough, we get the same value for moles. We get 0.04 for copper and 0.04 for water. Now that's really important because that helps us with our ratio. They are in a 1-to-1. Same value effectively. The only equation that could give us a 1-to-1 is equation 2. So that's how I know it's that one. And the marks come from calculating the moles, working out the ratio, and saying which equation is the correct one. So I know it's equation 2 is correct. I know it's the correct one because it's in a 1-to-1 ratio, because both the moles of the copper produced and of the water are both 0.04. Hopefully that helped you out today. If you want any other types of questions, limiting reagent questions, longer answer questions, shorter ones, if you want any of those, pop them in the comments below and I'll happily do another video. But thank you for watching. See you later, guys.